Hello, my name's Greg Nolan. I'm Director of the Centre for Sustainable Architecture with Wood, and this is my colleague Azin Atali, and she is a postgraduate student here in the centre.
I'm just working specifically on eucalyptus nitens plantation to make a suitable product for building application.
So this material here in front of us is a plantation hardwood material, and these boards have been recovered from a fibre managed resource. The fibre managed resource has a number of relatively consistent characteristics. It's been quite quickly grown. The trees have been grown close together, and they feature a whole range of strength reducing characteristics which are quite obvious in the board. This limits their potential in some applications, but it still means that they're useful in other applications.
So strain reducing characteristics such as knots and juvenile wood can reduce the structural capacity of the timber boards for building application. However, they can still useful to be used in mass timber products for structural application.
So while it has been grown specifically for fibre, the trees that make up the bulk of Australia's plantation resource can still be converted into solid wood products, either as board, as we can see here, or into veneers. That doesn't mean we know how to do all of that now. We only know how to do a bit of it. So here we've got resource from the two major species out of Australia's plantation hardwood estate. This material here is from eucalyptus nitens material. It was probably about 20 to 22 years old when it was harvested. This material over here is from a eucalyptus globulus stand that I think was about 24 to 26 years old when it was harvested. The relative age of the two materials doesn't matter that much at this stage because we don't quite know enough about the way in which age and site interact to know that the properties of one compared to the properties of other are going to vary that much between ages of about 20 through to about 25, 26. One thing you'll notice from both of these though is that the material can be cut and planed and then used as a reasonable quality board. So this is a nitens board. You can see it is from an unthinned, unpruned resource because it's got a series of natural characteristics in it. This stuff's actually quite relatively clear compared to the bulk of the material that we've been able to process. This material here is from eucalyptus globulus resource, and it's also got a series of strength reducing characteristics, but again there is enough reasonable quality material in here, and the base characteristics of the timber is such that it's still very useful for a range of structural and other applications.
I think in terms of the strain reducing characteristics, they are almost similar. So we have features such as knot in both of the material, and also in terms of the density, they're almost in the same range. I and my colleagues have done extensive work and research on this material to make mass timber elements, and also we can compare the value we calculated from the different products to the European and Canadian standards with softwood species as well.
In 2016, Seesaw secured funding from Forest Wood Products Australia to look at manufacturing mass laminated timber panels using nailing from a range of Australia's plantation hardwoods. That's both nitens and globulus. On the photographs you can see here on the left-hand side, we've got the globulus logs on the sawmill deck ready to go in to be converted into board. Nominally 38mm board of a variety of widths. On the right-hand side photograph, you can see some of that board in the pre-dryer from the processing company. Now, the thing about Knightons as a species and globulus as a species is that they're both collapse prone. That means during drying, the cells collapse in on themselves and you get characteristic distortion of the board. And if you look at that photograph, you can see that there's some ripple lines across the faces or the sides of the boards, and that's a characteristic indicator of collapse. So one thing we know from a range of work is that the plantation material tends to collapse reasonably quickly and can be quite dramatically compared to some of the denser native forest material. However, that collapse can generally also then be recovered through a process called reconditioning. In this photograph on the right-hand side, you can see the same E-globulus boards that have been reconditioned and the racks being broken down. So you can see that the board has recovered all of those particular shapes and they're now relatively rectangular board. That material was dressed. It was then graded as part of the research process on the right-hand side, then as boards that each of which has a known modulus of elasticity. That's a known stiffness. Those boards then were converted into a series of nail laminated panels, and you can see one of those in the photograph on the left. That particular type was then fitted with commercially available shear connectors, and there was a concrete topping put onto that to mimic what you might do in a commercial or a high-end residential building, and then that material was tested. Now, all the results of that are available in the FWPA report, which can be downloaded from their website. Concurrently with that, some of that material was then converted into CLT panels, and the CLT panels were tested for both strength and stiffness, and the results of that was also then published. If we look at how the Knightons and the globulus perform to other major species that are available or have been reported in the literature, we can see it here in these two tables. The top one shows us the modulus of elasticity, that's the stiffness of nail laminated timber panels, compared to the bottom one, which is the modulus of rupture. That's when it breaks under load. So what we can see is, particularly in the globulus in the top chart, we can see that the globulus performs reasonably well against all the other major species, hemlock, spruce, etc., which is then being used experimentally or used in the marketplace to provide mass laminated timber products such as CLT and glulam. If we come down to the bottom one, we can also see that the MOR is also pretty good compared to quite a number of those other species. In summary, from Seesaw's previous work, we know that suitable logs can be satisfactorily milled to board. That's given that we understand that globulus is a collapse-prone species. Then these boards can be sorted into structural groups. That doesn't mean that we can use Australian standards to do that, because Australian standards were developed for something else, not for plantation hardwoods. So there's going to need to be new standards developed for how we grade this stuff. But we do know that these groups can be assembled into mass timber and other useful engineered wood products, such as glulam. And we know that experimental batches of these products can perform satisfactorily. An important thing, though, is the results of one batch of logs from northern Tasmania doesn't represent the performance of the broadest E-globulus estate. Most of the E-globulus in Australia comes from WA and South Australia. And if we want to understand how this material is going to perform as an engineered wood product for domestic building processes, then we've got to sample those both estates and the board that comes out of those estates to see exactly how they compare across region and how then we can best process them to make reliable products.